Hi, welcome to Physics for Engineers. This is another video wherein we will tackle some of our example or sample problems. Let's go! Hi guys, so we will now continue our second part of our Newton's laws of motion. We will have second law of motion sample problems now. But before anything else, I just want to make a correction on our sample problem for not Newton's first law, but for motion in 2 dimension. I want you to go back to number 13 again. I made a boo-boo. I interchanged my positions. It should be delta R, that is equal to R2 minus R1. So I have 14 cm I hat plus 10 cm j hat minus 4 cm I hat. And doing this operation, we will have delta R, that is now 10 cm I hat plus 10 cm j hat. And then for calculating the average velocity, so we have to correct the delta R. So we have now the average velocity 5 cm per second I hat plus 5 cm per second j hat. And getting for the magnitude of our average velocity, we have 7.07 cm per second, and our theta is just equal to 45 degrees. It will still follow our rules in significant figures. Okay? So let's have Newton's second law of motion. That is sample problem number 6. Okay? So Newton's second law of motion. 3 sleds are being pulled horizontally on frictionless horizontal ice using horizontal ropes. The pull is of magnitude 190 newtons. Find A, the acceleration of the system, and B, the tension in the ropes A and B. So for all we know, this is already our standard operating procedure when we have laws of motion for any problem that wherein our particle is subjected to a force. It is better for us to illustrate our free body diagram. So I have here the three body diagrams. I have here the FBD of my 30 kilogram, my FBD of my 20 kilogram sled, and FBD of the 10 kilogram sled with the corresponding forces. So I don't want to reiterate again on what are those forces that we have to be mindful of. We have that one in our Newton's first law of motion. But I just want you to take notice of this one, that since our system is accelerating, so we have accelerations here. And then it is better for us to take note where our acceleration is pointing. For this one, I just assume that my acceleration is going to the right. Okay, so I have my acceleration to the right of the 30 kilogram mass going to the right. Same thing with 20 and 10 kilograms. And now we have this sample problem number 6, that they are just being put, these masses or these sleds are just being pulled, and then they are moving at the same time. So meaning to say, my 3 accelerations here are just the same. So I just take note of this one as AX. Okay? And then it will follow second law of motion. So let's solving for letter A, finding the acceleration. So it's kind of difficult to get the acceleration using this only, the free body diagram of 30, of 20 alone, or of 10. I have to actually mix them all together. I have to make use of 30, 20, and 10 kilograms. That's one method. But there's also another method in solving for the acceleration, and that is because this is just a one system, and I could treat this as one system wherein I have 30 plus 20 and 10 kilograms mass that is moving at the same time. And then I have only the net force that is just equivalent to the pull. I did not take notice, or not take notice, I did not account for the tensions in a B and in chord A. Okay, I just neglected them first. But for me, I want to be proper, and then I want to show wherein let's not forget about tensions B and A. So I denoted my tensions as FB and FA. Okay? The second law of motion, summation of forces is equal to MA. So it will follow summation of forces sa Y is equal to MAY and summation of forces sa X is equal to MAX. Okay, let's just have this one so that I will not be repetitive with this one. Actually, we could make use of this law by in analyzing our free body diagram and analyzing our system. But we have to know that we don't have acceleration along the Y. Our system is not jumping up and down. Our system is not under free fall. So AY will just be equal to 0. So even though this will follow second law of motion, we could still denote this one as like this along the Y, AY, but AY is just equal to 0. So that's why there are instances, some books, they noted it as, even though second law of motion, summation of forces, so Y is just derecho equals to 0 because AY is just equal to 0. But for us here, for summation of forces sa X is equal to MAX. AX is not equal to 0. It is equal to something. Okay? So let's have the free body diagram of 30 kilograms. So summation of forces sa X. I have FB equal to M30AX. I cannot get the acceleration there because I don't know FB yet. So note that as equation number 1. For the 20 kilograms, I have negative FB. I have positive FA equal to M20AX. Mass of 20 times acceleration of the X. Number 3, or note it as equation number 2 rather. And then for equation number 3, I have FBD of 10 kilograms. So I have negative FA plus positive F pool, or positive F pool is equal to M10 times AX. So as you can see, I have here unknown MB and AX. Here, I don't know, FB, FA, AX. I have three unknowns. And the last one, equation number 3, I don't know, FA and then AX. I have 3 unknowns. Meaning to say I should have 3 equations. Well, as you can see, we already have the 3 equations. So we could solve our acceleration from these 3 equations simultaneously. We're solving them simultaneously. So I just start with equation 1. I will substitute equation 1 into equation number 2. Hence, I have this one. Doing algebra, I have FA equal to M20AX plus M30AX. So let that be equation number 4. Because we cannot solve yet for acceleration X because we don't have FA. So from this one, number 4, from equation number 4, you substitute this equation number 4 into equation number 3. So we will be left with this one, negative M20AX plus M30AX plus FP equal to M10AX. Doing the algebra and then substituting our values, we only have AX left on one side of the equation. So AX now is just equal to 3.167 meters per second squared, or by sig figs 3.2 meters per second squared. That is now our acceleration. That's our answer for letter A. Next, for letter B, the tension in ropes A and B. So we just have to inspect our equations again. I can solve for FB and FA just by substituting acceleration. I can solve for FA just by using equation number 4. And then I will substitute AX. Then I could solve for FB by substituting AX here in equation number 1. So I will do that one. So let's have FA. FA, sorry. I will be using equation number 4 for FA for that one. So FA now is equal to M20AX plus M30AX. Substituting AX, I use AX, that is 3.167. I will round off at the on the last part. That's the answer. So I will now have the answer, that is 160 newtons. Next is my FB. FB is just coming from equation number 1. FB is equal to M30 times AX, so that is 95 newtons. So that is for sample problem number 6. It's actually kinda easy for solving for this sample problem. Now, let's have this problem. Next problem, number 7. This problem is actually coming from our first law of motion. That is last, I think, sample problem number 5. Now, we will just have another variation of it. Consider the system shown. Block A weighs 45 newtons and block B weighs 25 newtons. Once the block B is set downward motion, a cat also weighing 45 newtons falls asleep on top of block A. If block B is now set into downward motion, what is its acceleration, magnitude, and direction? Okay, last time from sample number 5, our system is under first law of motion, constant acceleration. But this time, there's a cat that is asleep on top of box A. So it changes the acceleration. So we should solve for the acceleration, both of the magnitude and direction of that acceleration. Again, free body diagram. If you have A and B, so you also have two free body diagrams for this one. So as an SOP, we have the free body diagram of our sample problem number 7. So we have two systems, two blocks. So we have two free body diagrams also. So you have FBDA and then FBDB. For FBDA, it will be different from the previous sample number 5 because we have an additional weight, and that is the additional weight of the cat. So that's why we just added, or I just added in the free body diagram, or in a vector that's pointing downwards. So it's FG of the cat. Okay, the gravitational pull for the cat, right? And then for the acceleration AX, I just pointed it towards the right because my force Ft is going to the right also. And if you want, there are instances, there are people that I don't want my A pointing to the right also. I want my acceleration pointing to the left. It will be okay also, but later we will have that one. There's a meaning to it. If we could get a negative acceleration or a positive acceleration direction, there are meanings to it. And then for the free body diagram of B, block B, we have the usual, the tension force, and then the pull of gravity kay block B. And then we have the acceleration along the Y. I will note it as A lang din, but pointing downwards. So if downwards ito, and then we're familiar already with positive X and then negative Y, so meaning to say, we're pointing towards the negative Y direction. Okay, so we have to account for the negative later. But this one, I'm just after the magnitude, and my vectors are telling me in what direction they are going, the acceleration is. Just note, just take note of this one, that they are connected via cable. So meaning to say, if block B has an acceleration, let's say for example 1, so block A also has an acceleration of 1. So they have the same acceleration. That's why I just denoted it as acceleration A, and then dito then as A. So I could have the same values for acceleration in terms of magnitude, but obviously later on they have different directions. Sige, following second law of motion, summation of forces is equal to MA. So we now have this one. So summation of forces to X is equal to MAX, summation of forces to Y, MAY. Where in terms of magnitude, AX is just equal to AY equal to A. For this particular example only. Okay, so using the free body diagram of A, so summation of forces to X is equal to MA. So I only have Ft equal to what is the total mass that is accelerating, and that is the mass of the cat plus the mass of the block A times acceleration. So let that be equation number 1. Using FBDB, summation of forces along the Y is equal to MAY or MA because of this one. So we have Ft minus FGB equal to the mass of the accelerating body, and that is MB, times negative of A because it is pointing downwards. for our direction. Now, what we're going to do is we have to substitute equation 1 going to equation 2. So, we now have this working equation, and then not substituting, rearranging, because we want to get the acceleration A. So, just take note that we have the weight or the gravitational pull that is just equal to mass of the object times g. So mass is just equal to Fg over g. So from this equation, we have to get a acceleration. We now have this working, not working. We now have this final equation wherein we will substitute everything. So 25 newtons all over, 45 newtons plus 45 plus 25. I'm already given this one. I'm given the weight of my objects. I have the mass, the weight of the cat, 45, the weight of block A, 45, and then the weight of our block B, that is 25 newtons, all over 9.8. Okay, I did not do this operation one by one. I just make use or take advantage of my calculator because I could use this one already as one diretso. So acceleration now is equal to 2.1 meters per second squared. So block we got a positive acceleration, meaning to say the assumptions for our accelerations are correct. So meaning to say it is pointing or going, or block A is going to the right, while block B is going down. Now, what if we got a negative acceleration? What will happen? If we got a negative acceleration, our assumption might be the direction might not be correct. So meaning to say, if we got a negative acceleration, our block A should be pointing or going to the left, and our block B is going up if we got a negative acceleration. So please be careful if you got a negative acceleration. So my tip for you is that if you got a negative acceleration, you check your solution. Did you made all the necessary na derivation? Have you forgotten about the about transpositioning of your variables? Have you forgot to add, or you forgot that it should be negative? So you have to check on them. If you're confident that there's nothing wrong, then your assumption that it should be not going to the left, or not going to the right, but going to the left. Okay, but for this case, we got a positive value that is 2.1 meters per second squared. So our assumption is correct. Block B will have an acceleration of 2.1 meters per second squared in the negative y direction, because we are to solve for the acceleration of block B, and the acceleration of block B with its magnitude and direction. Okay, so that's for sample problem number 7. Let's have sample problem 8. I thought this is a hard or difficult problem, but it's not. This is an easy one lang pala. So, with different scenarios lang. A box with mass 10 kilograms moves on a ramp that is inclined at an angle 55 degrees above the horizontal. The coefficient of kinetic friction between the box and the ramp surface is 0.300. Calculate the magnitude of the acceleration of the box if you push on the box with a constant force that is 120 newtons that is parallel to the ramp and the ramp surface. And then you now have these conditions or scenarios. A, if you push it parallel to the ramp and A directed down the ramp, moving the box down the ramp. B, if you push it parallel to the ramp surface, directed up the ramp, moving the box up the ramp. So we have to solve for the acceleration. So this is our scenario for number 8. This is our illustration, by the way. So if you push it downwards, it will move downwards. If you push it upwards, it will move up. Okay, so let's have letter A. So FBD of the box for part A. So, pointing down ang pag-push. So, you have now your free body diagram. You have your pull of gravity. And then you have the pull force that you did that is pointing downwards, down the ramp. You have your normal force. That's it. That's for your 3, 4, 6. And then you have your acceleration. I'll assume that my acceleration is pointing down the ramp also, or pointing towards the negative x direction. Okay, so we have to decompose our vector fg into components fgx and fgy. We now have this two. Okay, so please review if you forgot about how to get this one and why this is 55 degrees. That's from our previous example. Not example, from our previous sample set of problems. So, second law, summation of forces is equal to MA. Let's start with this free body diagram along the x. So, you have summation of forces sa x is equal to MAX. So, you have negative FP, negative FGX, and then positive FK. Sorry, I forgot to mention. You have kinetic friction pala. So, positive FK equal to mass of the block, of the box, times negative AX, negative acceleration, because it is pointing towards the negative x direction. And then we have to solve for the acceleration. I just put it AX now. I isolated AX. So AX is equal to FP plus FGX minus FK over M. So I have to solve for FK first because I already know FP, and then I can solve for FGX already. So FK, where solving for the friction force, kinetic friction force is always equal to the coefficient of friction times the normal force. So I don't know the normal force yet, but I can solve for the normal force using summation of forces along the y. So summation of forces along the y is equal to MAY, wherein AY is equal to 0. So we have normal force minus FGY. So Fn minus FGY equal to 0. So Fn is equal to FGY, wherein Fn is just equal to Fg cos 55. So Fk, solving for Fk, it is just equal to mu k times Fg cos 55. So this is pull of gravity. So Fg is equal to mg. So we have now the acceleration Ax is equal to Fp plus Fg sin 55 minus mu k Fg cos 55 all over m, the mass. Okay, and then substituting substituting what we know. So we now have this one. So Ax is equal to 120 newtons plus 10 kilograms times 9.8 meters per second squared sin 55 minus 10 kilograms times 9.8 cos 55 all over 10 kilograms. So we now have an acceleration that is 14.4 meters per second squared in the direction of the negative x direction. Okay, so that's for letter A. If it is directed down the ramp and moving down the ramp. For letter B, what if you push it upwards? So we now have the friction, not the friction, we now have the normal force, the pull of gravity, and then you have your pull that is upwards, going up the ramp, and then our motion is going up, so the friction force is in the opposite direction. So I'll assume that my acceleration is pointing up the ramp. So SOP again, FGX and FGY. So solving for the acceleration, summation of forces sa x is equal to MAX, wherein this time AX is just equal to a positive value. So negative FK minus FGX plus FT is equal to MAX. So AX is equal to negative FK minus FGX plus FP all over the mass. And again, we don't know Fk, so solving for Fk, the same thing with what happened from letter A. So Fk is still the same, UK Fg cos 55. So Ax now is equal to this one, negative mu k Fg cos 55 minus Fg sine 55 plus Fp all over the mass. Substituting all the variables that we know, so the acceleration now is positive 2.29 meters per second squared in the direction, the positive x direction or positive x axis. So that's for sample problem number 8. So it's kinda easy. They just have different scenarios. Let's have number 9. This is an easy problem again. Also, they are just the same with our sample problem from last time, but this time it is accelerating. A light rope is attached to a block with mass 4 kilograms that is at rest on a frictionless horizontal surface. The horizontal rope passes over a frictionless massless pulley and a block with mass m that is suspended from the other end. When the blocks are released, the tension in the rope is 15 newtons. A. Draw the free body diagrams of each of the block. B. What is the acceleration of either block? C. Find the mass m. And D. How does the tension compare to the weight of the hanging block? So, the scenario, ito. So, on a frictionless surface, you have a block that is connected to a rope that is passing on a frictionless pulley, wherein another block is hanging, that is B, with an unknown mass. Okay, free body diagram for each block. You have this one. So you have for block A, the normal force, the tension force, and then the pull of gravity. And then we have block B, tension force, and our pull of gravity for block B. For the acceleration, kayong bahala if you want it in the opposite direction, compare it to my direction, but okay lang din the same tayo ng understanding. Better ako na if there's an object that is hanging, my acceleration will follow the direction where it is moving. So I will just have it moving downwards. I will just assume that it's moving downwards. So my acceleration for block B is going down, while my acceleration for block A is going to the right. Syempre, hinihila ni B, si A. Okay? Their accelerations, their magnitudes are just the same, but they have different direction. Okay, so that's for letter A. For letter B, solving for the acceleration of the block. So, I will start with summation of forces equal to MA. I will start with FBDA. So, summation of forces X is equal to MAX. So, that is just Ft is equal to MA plus acceleration A. So, acceleration is just equal to Ft over MA. So, that is 50 newtons over 4 kilograms. So, you now have the acceleration. That is 3.75 meters per second squared. That is for the magnitude of the acceleration only. So, for box A is moving at a rate of 3.75 meters per second squared in the positive x direction. Meanwhile, box B will have the same magnitude, 3.75 meters per second squared, but in the negative y direction because it is going downwards. Okay? So, that's for our letter A. For letter C, finding mass M. Obviously, for that mass, that unknown mass, you could solve that one using the free body diagram of B. So, using that one, summation of forces along the y is equal to MAY. So, you have the tension force. You have the tension force, and then minus the pull of gravity is equal to MB times the negative A, negative of acceleration. So, where solving for the pull of gravity or the weight of block B, you have FGB is equal to MBG. So, we now have FT minus MBG is equal to negative MBA. I want to get MB, so manipulating this equation, I will be left with this one. Okay, so you now have tension force is equal to mass of B now is equal to tension force all over gravity minus the acceleration. So I have 15 newtons all over 9.8 meters per second squared minus 3.75 meters per second squared. So mass MB is equal to 2.479 kilograms, or mass M, same thing with mass M, I will just have to round it off. I now have 2.48 kilograms. Okay? For letter D, how does the tension compare to the weight of the block? So solving for the weight of the block, so FGB is equal to MVG, so that is 24.3 newtons. So comparing it with FT, 15 newtons. So as you can see, the weight of the block B is heavier compared to the tension force that is 15 newtons. So it will really have to go downwards, because for this one, if you're going to get the net force, you have positive 15 minus negative minus 24.3, you'll get a negative net force. Negative net force means to say you have a negative direction for your acceleration, so it is going downward. Okay, what if they are equal? Well, it's kinda counterintuitive, because if it is equal to, if they are just equal to each other, block B should not be accelerating. Okay, so that's for sample problem number 9. Sample problem number 10. Well, problem number 10, I thought this is difficult, but it's very easy lang pala. So, two blocks connected by a cord passing over a small frictionless pulley rest on a frictionless planes. A. Which way will the system move when the blocks are released from rest? B. What is the acceleration of the blocks? And C. What is the tension in the cord? For letter A and B, I will be solving it simultaneously, because if I can solve for letter B, I could know the direction of the motion of our system. That's letter A. Okay? So, free body diagram. So, you have here two free body diagram. I have the FBD of 100 kilogram, and then I have the FBD of the 50 kilograms. Yan. Okay? So, this one. Now, I have here the normal force. For the 100 kilogram, I have the normal force. And then I have the pull of gravity, or the weight. I have the tension force here. Now, I denoted my acceleration, that is sliding down the ramp. The ramp on of the 100 kilogram, that is inclined at 30 degrees. So I have my acceleration in the negative x direction, so ax equal to a with the negative direction. For the 50 kilograms, I have the normal force here, the pull of gravity, or the weight, and then I have the tension force. Since I denoted my acceleration for block 100 kilogram, that is sliding downward, so they are just connected by the same wire. So 100 kilograms will pull the 50 kilograms. So the acceleration for my 50 kilograms is pointing up the ramp. Okay? But take note also that my x and y axis, they are not the same for both of the blocks. I have here my x and y. I have the positive x and the negative x, positive y, negative y. Meanwhile, for my 50 kilograms, this is my x and y. I have your positive x, positive y, negative x, and then negative y. Okay? Just be careful with that one. So, we have to decompose the pull of gravity. So, we now have these four equations here. Okay? So, let's solve for letter A and letter B. Second law, summation of forces is equal to MA. Since this is frictionless lang, I will not be solving for the normal force. And then I don't have acceleration along the y, AY is just equal to 0. So I will go directly to summation of forces along the x-axis. Okay, so using the 100 kilogram free body diagram, summation of forces is equal to MAX. Wherein for this one, my AX here, now this one, is negative. Okay, so I have negative FG1X. I have positive tension Fp, and then equal to M1 times the negative of A. Okay? So Ft is equal to Fg1x minus M1A. So cannot solve anything, so let that be equation number 1. Now, using free body diagram of the 50 kilograms. So summation of forces sa x is equal to MAX. So we have negative Ft, we have positive Fg2x, and then we have the acceleration that is negative. So negative Ft plus Fg2x is equal to M2 negative A. So I will be now simultaneously solve for these two equations so that I could get for the acceleration. If the acceleration is positive, meaning to say my assumption of my motion is correct, but if it is negative, then it should be moving the other way around. Both block 100 kilograms and block 50 kilograms. So solving for acceleration, we now have this equation. So rearranging to get for the acceleration, you can now substitute your values here, your known values. So this will now have, acceleration is now 0.6543 meters per second squared or 0.7 meters per second squared. And that is now our acceleration. The acceleration of our block 100 kilograms and block 50 kilograms. They will have the same acceleration. But for the direction where block 100 kilograms is going, it is now going down the ramp, or going to the left side of our x and y axis. But for the 50 kilograms, it is going up the ramp. Okay? So that's for letter A and B. Solving for the tension force Ft, I have this conclusion pala. Okay? So solving for our tension force Ft, you could use equation number 1, wherein that is just Ft equal to Fg1x minus M1a, substituting Fg, that is mg, times sin 30 minus M1a. We now have the tension force that is 424.57 newtons, or approximately 400 newtons. Okay? 1 sig figs lang kasi. So that's for sample problem number 10. So we now have the last example. The last example number 11. This is circular motion. A small remote controlled car with mass 1.60 kg moves at a constant speed of v, that is 12 meters per second, in a track formed by a vertical circle inside a hollow metal cylinder that has a radius of 5 meters. What is the magnitude of the normal force exerted on the car by the walls of the cylinder at A, point A, bottom of the track, and B, point B, top of the track? Okay, this is actually similar to your sample problem in your textbook. That is the last problem, the one that is on the Ferris wheel. Okay, so let's have the free body diagram. You have two scenarios here. The free body diagram at the bottom, at the bottom and then at the top. So you have the normal force pointing down upwards, and then the gravitational force pointing downwards. And then your radial acceleration is pointing towards the center seeking kasi yan. So towards here. So I have that radial acceleration. For the free body diagram at the top, you have still the normal force pointing upwards, and then the pull of gravity pointing downwards. And your radial acceleration is center seeking. Since nasa taas, so the radial acceleration is pointing downwards towards the center of our roller coaster, or of our track. Okay? So, for radial acceleration or for circular motion, we have a rad that's equal to 4 pi squared r over t squared. But we are not given in terms of the period for us to solve for the radial acceleration. But instead, we are given the linear velocity, or linear speed rather, that is 12 meters per second. So we could actually make use of the one that is already derived, coming from this one. So summation of forces or net force is just equal to mv squared over r. Okay, so using block A, not block A, but FBDA, summation of forces equal to mv squared over r. So looking at this one, you have positive normal force, negative Fg. So negative Fg plus the normal force positive equal to mv squared over r. Just take note that this is pointing up, so this should be positive. Okay, so solving for the normal force, derive this equation so that you could arrive with this one. Okay, so solving for that one, it is already given. The normal force at the bottom is 61.8 newtons. Meanwhile, for the free body diagram, for the solution for letter B, wherein the normal force at the top, so you have this one, Fn minus Fg is equal to, ito lang ang kaibahan, negative na dapat si radial acceleration. Because you have a center-seeking na radial acceleration, it is pointing downwards. Okay? So, you have a negative radial acceleration. So, we now have this working equation. Solving for that one, the normal force is actually negative 30.4 newtons. Okay, negative 30.4 newtons. But we're just asked for the magnitude, we now have 30.4 newtons. Actually, it is expected na we have a lesser normal force at the top compared at the bottom. Okay, because we have another forces acting on our toy car, and that is we also have the seat belt. If you want, we could have, because it is very fast, and then it will just move diretso dito pababa, biglaan. So we now have this one, 30.4 newtons. So that's for our sample problem 11. So that's for this set, second law of motion. So thank you for listening.